In this video, we're going to talk about something called the coefficient of determination and what that means and how it relates to whether or not the straight line we found with the least squares regression, if that actually is going to be a good fit for our data. Now, before we can get into that, we have to talk about something called deviations. So you want to think about, we have data, right? And data is going to be spread out. There's going to be some sort of average value of the data. And if you want to say how far away is the specific data from the average, that's your total deviation. So the total deviation, that is how far away the actual data value is. Sorry, should just be a y there. Minus the average value. So how far away is this actual data from the average value of the data? That's the total deviation. Now, we're going to be able to break that up as follows. The total deviation is y minus y bar is going to be broken up as y minus y hat plus y hat minus y bar. So you see, I kind of just added and subtracted the same thing. If you were going to simplify this in math, right, you would just cancel out the two y hats there. But regardless, it is the same as the original total deviation. And this part over here, this is y hat minus y bar, we are going to call this the explained deviation. Because the idea is we have our approximate straight line based on y hat. And if we say y hat minus y bar, that's the deviation from the line compared to the average value y bar. And we can explain why those two numbers are different because we have this line. We know exactly why the line is off there because of the slope and so on. So that means this part over here that is the difference between the actual value and the approximated value, that we can't talk about in terms of slopes and intercepts. We don't really know why they're not the same other than kind of randomness. That is going to be the unexplained deviation. So we can break up total deviation as the unexplained deviation plus the explained deviation. And it turns out mathematically you can prove that if you were to take all of the total deviations, square them to make sure they're all positive, add them all up, that's the sum of all the total deviations there, and then we call that the total variation. You can rewrite this as the sum of all the squares of the unexplained deviation, which we call that the unexplained variation, plus the sum of all the explained variation, which is, the sum of the deviations and the sum of the deviation squared is the variation. So it is not necessarily straightforward why this would be true based on the previous statement. You just kind of have to trust me here. So we can look at the individual deviations, break it up into unexplained and explained. If we then kind of total each one of them to get the total variation, the unexplained variation, and the explained variation, once we have that, we can define what this capital R squared is, which is the coefficient of determination. It is defined as the ratio of the explained variation divided by the total variation. So this is saying that what percentage of all the variation that you're seeing in your data is explained by the linear regression. And so if this number is close to 100%, that means that we are explaining almost all of it based on our straight line. That means our straight line is a good way of talking about the data. If we do this and we get, say, 10% for R squared, well, that means that our straight line is only explaining 10% of what's going on, and that's not very effective. So the bigger the R squared number you have, the more effective, the better fit your data is to the straight line you found. Now there's something that I think is kind of cool here, that we have this big old complicated calculation for r squared. And previously we did have something called little r that was separate, called the correlation coefficient. And it turns out, at least in this case that we're doing in our class, it's not always true, but in our case, capital R squared is actually the same as little r squared. And so instead of having to calculate all these deviation things in order to figure out what capital R squared is, we can just take our correlation coefficient, which our calculator already gives us, square that number, and bam, we have our capital R squared now, because they are equal in this scenario, in this class. Now, when you have more than two variables, it gets more complicated, but for just the two variable case, x and y, this is what we have here. And I want to kind of point out, remember I said if your r is about 0.7, that was kind of good enough. Well, what happens when you square that? 0.7 squared is 0.49. So if you're even a little bit bigger than that, that means your straight line is going to be explaining more than half of what's going on in your data, and that's enough for us to say it's a decent approximation. Obviously, half is not great, but the further you get, the higher value of r and r squared you get, the better approximation it's going to be. So you just kind of do what you can here, but 0.7 is kind of the cutoff because r squared is almost about 50% there. That's where it came from. So this is trying to understand what this capital R squared is, what it means, and how we can use it to decide whether our straight line is actually a good fit or not.